All right, so Unit 2, functions. Here we go. Nice, quick, easy unit. If I remember correctly, it's the easiest unit. So, should get some good grades this one, right? Should get some good grades. We start the unit with function notation and domain and range. Good old Algebra 1 type stuff. A function, and this they actually teach in Algebra 1, a function can be thought as a machine that turns inputs, which are usually x's, into outputs, which are usually the y's. We'd say x is the independent variable and y is the dependent variable, but you plug in an x and a y falls out. For example, let f be the function that will convert x into 2x plus 3. Well, this can be written as two different ways. So it could have been written as, it could have been written as f of x equals 2x plus 3. Or it could have been written as, and I'm going to have to get a little creative with space here, it could have been written as f such that x maps onto 2x plus 3. That's just a fancy way of saying all your x's get plugged in and they come out as a 2x plus 3. Okay, so as long as you're comfortable with both of those formats meaning the same thing, you're in good shape. Well, in math speak, all those symbols replace words. Because mathematicians aren't trying to write all that stuff, so I was saying what those symbols represent. So it says f such that x maps onto 2x plus 3, so all the symbols have words. But basically, you plug an x in and a y comes out. So f of x is the value for y. So we would usually say y equals f of x. Whatever, that's all just nomenclature and things like that, just naming stuff. Nothing crazy is going on. So let's start with the really, really easy. We've been told that x maps onto 2x squared minus 3x. That means you plug x's in to where it says x squared and where it says x. So if it says find the value of f of 5, showing the work would look like this. F of 5 equals 2 times 5 squared minus 3 times 5. Right? Just wherever there was an x, you replace it with a 5. Just watch your order of operations and you'll be okay. So does it give us 2 times 25? That's horrible. Minus 15. 50 minus 15. Oh, 35. Okay, cool. Yeah, 35. Yes, way. So am I going to be having you plugging in numbers on your test? Probably not. This is extremely basic. We're going to scaffold our way up to what we want you to be able to do with it. Part B says plug in -4, so I'm going to do the exact same thing. I'm hoping that you notice that when I substitute, I used parentheses. You should too. It's going to help you get your accuracy points and things like that because you're less likely to mess up negative signs and things like that as long as you're using your parentheses. So order of operations, have to square that -4 first, giving us a 16. And then when you multiply two negatives, you get a positive. So we have 32 plus 12, or 44. Basically, it works like this. Whatever I put inside the parentheses in I call it the function notation rule, whatever I put inside the parentheses, you put that number inside parentheses. So wherever you had an x, I put a set of parentheses, and I put stuff in those parentheses. And the reason why I say it like that is because, well, in the next 3 examples, you're not plugging numbers in anymore. Instead, you're plugging expressions in for x. So if it'll help, I'll switch colors. Anytime I'm going to plug something in, I'll write it in red. Something that was replaced, I'll put in red. But every time, I will use parentheses where there used to be an x. And that is how you avoid negative mistakes and things like that. So we have a different equation. Now we're working with 5 minus x squared. So for part A, we are trying to find f of, and it doesn't matter what's going to go in here, because every time I saw an x, I'm going to replace it with a set of parentheses. So I have a 5 minus, there used to be an x here, minus something squared. There used to be an x there. So everywhere there was an x, I've opened a set of parentheses. and I'm filling those parentheses with negative x on the left and right. And I will not be able to fit all three of these examples on here space-wise because I have to write larger than you, so I will need to clear them to fit probably the third one, okay? Depends on the question. So standard form, no, you're good. Standard form, it depends on what the question's asking for IB. I mean, if they give it to you out of order like that, then you're okay giving them their answer out of order like that. But typically that doesn't happen, okay? So first, you've got this minus negative x. Well, that just means plus x. Two negatives makes a positive. Now, when we get to this next set of parentheses, though, you have to do the order of operations first. So you have to do that negative x quantity squared. Well, when you square a negative number, you get a positive number, and x squared is x squared. What it didn't do was change this minus sign, because what's inside the parentheses will square to become x squared. You just have to watch your order of operations. Part B, this one is also telling you to replace x with something. It's telling you to replace x with x plus 2. So everywhere there was an x, I will open a set of parentheses, and I will drop in that x plus 2. So once again, that minus sign in front of that first set of parentheses can be thought of as a -1. So here what we did was -1 times negative x. Well, here, when you have that -1 in the front, you need to distribute the -1 to the x and the 2. So we have 5 minus x minus 2 minus, and I am going to FOIL that x plus 2. Remember, x plus 2 quantity squared is not x squared plus 2 squared. Just reminding you that it would be x plus 2 times x plus 2, and you'd have to do the whole first, outer, inner, last jazz. But I am going to assume that we're all pretty good at that by now to save us the time. This gives us x squared plus 4x plus 4. I left it in parentheses for a reason, because once again, there is a -1 sitting in front, and that -1 does need to distribute to all three objects before you're finished simplifying. So we have 5 minus x minus 2 minus x squared minus 4x minus 4, and you would just combine all your like terms. And Luca, to answer your question, you see our x squared is negative. But since the question was proposed to us out of standard form, I say we just give it back to them in the same order that they gave it to us. So the 5 minus 2 minus 4 gives me -1. I see negative x and negative 4x, which is negative 5x, and then just a negative x squared. And there it is. Let me scroll so that everybody can see over their desk shields. I'll go back up to do part C. Questions, comments, or concerns with that kind of substitution? The reason why we're doing this function notation stuff is because, guess what we're doing this unit? Transformations. And transformations are all done using function notation. So the first one we did, f of negative x, this is, hey, all of your positive x's turn to negative x's. So if you were to have done that, let me grab handy dandy sticks. Even though we're not in the transformations unit, we might as well pretend we're there. Here we have sticks that represent the x and y axis. Let me start you here in quadrant 1 where the x's are positive and the y's are positive. It says all of the positive x's become negative x's. So literally it would have done, let's see if I can do it like this, from here to here. So you didn't know it yet, quote unquote, know it yet, even though you've learned it, hopefully. From here to here is reflecting over the y-axis. So that first thing you did was reflect over the y-axis. The next thing you did, if you were to have graphed the original f of x and then graphed that one, you would see that the graph shifted to the left 2 units. See, we're building up to transformations. We're probably doing those tomorrow. Can't quite remember, but that's what we're building up to. Okay. Screams of terror, if I clear these to do part C? Nobody will freak out? Okay. Because I need more space. Necesito más espacio. Come on, come on, come on. Catch up, catch up. There we go. And part C. This one's telling me replace all of my x's with an x minus 1, and there had better be a minus 5 stuck on the far right side. So if you treat it like an equation, I'll even do this one in black. If you treat it like an equation, there's a substitution where everywhere there was an x, now there's an x minus 1, and outside to the far right, there's going to be a minus 5. That's what that's telling me to do. On the right side of my equation, everywhere there was an x, I'm going to put a set of parentheses. Replacing those parentheses inside the parentheses with an x minus 1. And whatever you do to the left, you do to the right. There's the minus 5. There. I think the color helps. Sneak peeking. Replacing the inside with an x minus 1, that's shifting right 1 unit. And that minus 5 on the outside is shifting down 5 units. Major part of your upcoming test is transformations. Here, remember there's a negative 1 that you're distributing. So I have minus x plus 1. Now here, I'm going to write this minus sign. I am going to FOIL x minus 1 times x minus 1 again. And then there's the minus 5. Now just like last time, there is a negative 1 here that I have to distribute to all 3 places. 5 minus x plus 1 minus x squared plus 2x minus 1 minus 5. And again, they didn't give it to us in standard form, so I don't have to give them their answer in standard form. I do see that these 5s cancel each other out. These 1s cancel each other out. It would appear as though there are no constants in this one. I do see minus x plus 2x. So that just gives me plus x minus x squared. Wow, look at that. X minus x squared. Fun. So that would be the same parabola, just shifted right 1 and down 5. And like I said, we'll review transformations in an upcoming lesson. So far, so good? Yeah. Plugging things in, watching PEMDAS, foiling appropriately, that kind of stuff. So let's talk about domain and range. The domain of a relation is the set of x's that exist on it, meaning if you were allowed to plug an x in, that x is part of the domain. If you're looking at a graph, it's all of the x values that the picture quote-unquote covers up. What I like to tell students is if you could grab the graph and smash it flat onto the x-axis, which x's did it cover? The range is all the y values that it covers. It's all the y values that come out when you plug in x's. I want your domain and your range written in an interval notation, no less than or equal to type things, greater than or equal to. But on the test, it actually doesn't matter. But typically, we write our domain and ranges in interval notation. But since it doesn't matter on the test, IB doesn't care if you use interval notation or inequality notation. You can use whichever one you'd like because they're both acceptable on the test. All right? In the book, you're going to see all of the answers done in interval notation. And when I do my notes, I like to do things in interval notation. So for this first example, our domain, let me scroll down a little bit so people in the back can see what's going on. The domain for this one is all the x's it covers up. Again, if you smashed it flat onto the x-axis, it would do this. So the very first x that it covers, and it does include it because this is a closed dot, is the x value -1. So we do bracket -1, comma, since it points to the right forever, infinity. But this is the same thing as saying x is greater than or equal to -1. I should have done that in red since I drew a red arrow. Too late. And for this one, I'll actually use the correct color. The range is the y values that it covers up. Now, if you could take that black line and smash it against the y-axis, you would start there and go up forever. So its range, and I'll color coordinate appropriately, begins at the y value -3 and points up to positive infinity forever. Again, that would be y is greater than or equal to -3. For our second picture, if you could smash this graph flat against the x-axis, hopefully we'll notice that it points left and right forever. So it would actually cover the entire x-axis. So its domain is all real numbers. And the way we write that in interval notation is -infinity to positive infinity. All real numbers. If you could smash this thing left and right, smash it against the y-axis, this number right here would be where it starts and then it points down forever. So this thing's range comes up from -infinity. When you write your interval notations, it should always go small number to big number. -infinity is the smallest thing we can imagine, so we're going to write it as -infinity climbing all the way up to the number y = 1 and including y = 1. See, the bracket means it's included. Parenthesis means it's not included. You can never include an infinity because they're not real numbers. It's an idea. It's not a value. Sir? Yes, it is filled in. It's not an open hole. It's hard to tell on yours, but in there it's blue. On yours, I know it looks like it's just an open dot, but that's because the blue is so light that the copier probably left it as an open dot. Now, if it was an open dot, then our domain would not include the x value of 2, and our range would not include the y value of 1. Yes, Aaron?
So for example,
Mhm.
the range, wouldn't it be infinity -3?
Well, because infinity is so we always want to go small to big, and infinity is the biggest thing we can imagine. So we would say, if you ever have to say a positive infinities always end up on the right side. If you ever have to say a negative infinities always end up on the left side. Okay? And this last one, if you could smash it against the x-axis, smash it flat, it would go forever that way, but it would not hit this thing. So I'm going to put a parenthesis there, not a closed dot. That looks like an arrow. Hold on, I could do a better job. Like that. See, it doesn't actually hit that number of x = 2. It just gets really close to it. And the same thing is happening on the other side. It doesn't actually hit it. It just gets really, really close to it, but it does go to the right forever. So our domain, we start from the small. So since it starts from the far left, we can say, yes, it does shoot far left. So from -infinity all the way up to the number of x = 2. But it doesn't include it, so I'm going to use a parenthesis and not a bracket. Then I'm going to hop over the number x = 2 with this little union sign. And again, parenthesis, begin at 2 and shoot to the far right. So the parenthesis means does not include. So you see I am not including that x = 2 on either side. The range will do something extremely similar. And I would have to actually clear my picture for us to see it. So I will do that for good notes. Our range does the exact same thing. It does not hit this value of y = 1, but it does get really close to it. And it doesn't hit the value y = 1 on either side of it. Like that. So again, because we're going from small numbers to big numbers, we would come up from -infinity, get remarkably close to the y value of 1, but don't hit it, hop over it, begin at that number again without hitting it, and then shoot up to positive infinity, like that. So what do you think? Questions on interval notation, domain and range? Yes, sir. Brian.
So how do you know that it doesn't touch the 2 on the domain or the 1 on the range?
So the way we know it doesn't touch the 2 or the 1, x = 2 or y = 1, is because they gave them to us as dotted lines. What they're showing us is that those are a vertical and a horizontal asymptote. This kind of function, it's not important that you know this, but this kind of function is called a reciprocal function. So I know that we can never hit either one of those numbers. just because I know what the equation for that is, but I can tell you if they give you that dotted line, they're telling you don't touch that dotted line. Okay, that's how you know. Just keep making sure that I don't have somebody in the waiting room. Ready to go? Flip them. All right, flip them over. Boink. Let's see what's next. Exact same stuff. For each of the following graphs, state the domain and range. Now, once again, they have this dot filled in. This is a closed dot, and this is a closed dot. If you would like to, though, we could do these examples as if they're open dots this time, just to see how it would change the answers. You want to do that? Just to see? Let's do it. So let's pretend this is an open dot, and that this is an open dot. There we go. Now they're open. Open means we got dangerously close to that point, but we're not going to include it. So for our domain, all the x values that this thing can cover up, I'll do in red. Well, I can see that my x values begin at this closed dot, right? And they're going to go this way until I have an open dot here. That means I can't include that x value on either side of it. But then it will just keep going this way forever because I have no more open dots. Again, from small to big, our domain. From the far left, negative infinity. We always read our graphs from left to right. And go all the way up to the x value of 4, but don't touch it because it's an open dot. Hop over it with this little union symbol. Begin at 4 without touching it, and go to the right until you hit x equals 8. And since that is a closed dot at x equals 8, bracket. Questions, comments, or concerns on that domain of that picture? At all? Any at all?
I don't really know what my question is, but I'm not really.
So something about it's confusing you.
Yeah,
So just look at the answer and tell me which part are you uncomfortable with?
the 8.
The 8. The fact that it has a bracket, or the fact that it has an or that it is the number 8.
This is the number 8.
That's the number 8. Okay. So when we smash the entire graph, we grab it from the top and grab it from the bottom and smash it flat to the x-axis. Now imagine every single point is on the x-axis. So what are the y values there? If you're on the x-axis, what does y equal? 0. See, we're not worrying about it because at this point we've smashed it flat. They're all 0. All that matters are the x values when you talk about domain. And this one's x value is 8. And it gets a bracket because it's a hard closed dot. It's included. Okay, that better? All right. Now the range, same trick. I have a closed dot. So it begins here, and it goes all the way up until I have an open dot. That means I cannot include that y value. Like that.
On the other side, if it's
Right. Is that what you were going to say? So it looks like I can't include it because of this open dot, right? But like a couple of my gentlemen just realized, that point actually does get hit right here. So the question is, do I hop over it? But remember, you're smashing it flat. The question is, when I smash it flat, will that y value be covered up?
Yes.
Yes, it will. One side of the graph, it didn't cover it, but the other side, it did. So the question is it covered? The answer is yes. So its range then comes up from the number -2 and goes all the way up to infinity forever. And that does include the number y equals 3 because this side of the graph does hit y equals 3. Cool beans.
the old one.
And the next one being a parabola. This parabola has we made the vertex an open dot for funsies, just to see how it changed the answer. Let's smash it flat onto the x so that all that matters are x values. It's going to be all of these things to the far left until open dot. Now, because this thing is a function, that thing's domain does not include the number x equals 2. So that domain would be negative infinity, because that's far left, up to the x value of 2, hop over it, and then go from 2 to infinity. Interesting. Interesting concept here. A hole in a graph is actually called a removable discontinuity. Now, you don't need to know that for this curriculum, but that's what it's called, a removable discontinuity, which means that point could have been moved elsewhere. Now, you don't have to change your notes. I'm just showing you something. If that point had actually been up here at 2 comma who cares, which can happen sometimes, now the domain is all real numbers. Because again, if you smashed it flat, was that point covered? The answer would be yes. But that is not what we had, so I'm going to erase it. I'm just saying, if it's a removable discontinuity that jumped somewhere else, up or down, then just like what happened on this range, that x value would have been covered. But it's not right now. Now this one's range tries to begin, jokes, I forgot to change it to the pin. This one's range tries to begin at this y value, but it doesn't actually hit it because open dot. But it does cover everything above it. So its range would try to begin at -1, but cannot actually hit it, and then shoot up to infinity forever. Nerd, he says. Yes, sir.
So the open dot only changes the parentheses to a bracket.
The open dot makes a bracket turn into a parenthesis, because bracket means includes, parenthesis means gets darn close but doesn't actually include. So you know in Algebra 1 when you were graphing your dotted lines? Remember graphing dotted lines? You don't remember graphing dotted lines and shading half the graph and stuff like that? Okay. So the dotted line meant it was not equal to there, but that was the barrier. An open dot, and what you see here is telling you we're not actually equal to -1, but it is the barrier. It's the same idea. All right. Let's see what else we got today. State the domain and range of each of the following functions. Be honest with you, domain is the easy part. Domain is the easy part. So make sure they don't want us using a calculator. Nope. We're going to sketch these bad boys. That's what I thought. Okay. This first one is the square root. Tell me, what kind of numbers are you not allowed to take the square root of? Negatives. Well, here's what that tells me. Underneath the radical, since I cannot take the square root of a negative number, what's underneath the radical must be greater than or equal to 0. This will ensure that it's never a negative. 0 is allowed. The square root of 0 is 0, but negatives are not. So when you add 5 to both sides, what you get is x is greater than or equal to 5. Well, that's your domain. So from 5 to positive infinity. In order to see the range, I'm going to go ahead and draw a sloppy sketch. Okay, let's do that right now. 5. Picture not drawn to scale because who cares? We know that we can begin at, oh goodness, look what I've done. We know we could begin at the value x equals 5. And we said we can plug in any number bigger than 5. And how did I know it was on the x-axis? Well, because if you plug x equals 5 into this equation up here, which is why we started the notes with plugging numbers in, you get the square root of 5 minus 5, which is 0. Now I can go to the right. It says so. This says, oh, you can go to the right. You can go to numbers bigger than 5. Like, I could plug in the number 6 if I wanted to. Picture not drawn to scale. And if I plug in 6, I have the square root of 6 minus 5, which is the square root of 1, which is 1. So we get a graph that looks like this. And if you keep going, what you're going to see is a square root graph that looks something like that. Basically, it's half of a sideways parabola. So what is its range then? What y values does it cover up? You should just be able to look at the picture and tell me. What's the smallest y value it hits? 0, and it includes it and shoots off to positive infinity. There you go. Yeah.
And what did you put the five into to get?
Oh no, as far as when I plugged in 5, I got 0. I plugged in 5 right here and right here. So like 5 minus 5 is 0. And because this said I was allowed to go bigger than or equal to 5, I took the next number bigger and just plugged in 6. So I said, okay, 6 minus 5, it's 1. And the square root of 1 is 1. And wow, I did a really bad job of hitting my y value of 1 right there. I didn't even notice that. Sorry about that. Now this next one is a fraction. Fractions have one rule. Can't divide by 0. That's the one rule of a fraction, that the bottom is never allowed to equal 0. So you say x minus 5 cannot equal 0. So if you add 5 to both sides, you get x cannot be 5. And that's the only number it can't be. It could be every number except x equals 5. Well, that's your domain. You can write x can't be 5. That's acceptable to IB. But I'm going to be using interval notation in my notes because, well, I like interval notation. There's not really a better answer than that. So we're going to go from negative infinity up to the number 5. We'll get dangerously close, but we won't include it. Union, hop over 5, and go to positive infinity. Now, just like I had to do earlier, I will have to clear in order to finish part C, because I have to write large. And Brian, this is a reciprocal function, or we talked about it a minute ago. This reciprocal function will have a vertical asymptote at the value x equals 5, because I can't have it. But this will also have a horizontal asymptote, which we'll talk about in just a second. So let's see, drawing a quick dirty sketch. We know we have a no-no at x equals 5, can't do it. Well, I'm going to go ahead and draw that vertical asymptote. I cannot hit x equals 5. So we know there's a vertical asymptote there. That's just how that works. Anytime you're dividing by 0, vertical asymptote. It's just the way it works. Let's talk about plugging in a number remarkably close to 5. Just to the left of it. So let's talk about a number just to the left of 5, but remarkably close to 5. Like the number 4.99999999999. Remarkably close to 5, right? Now if I plug in 4.9999999 and I subtract 5, do I have a positive number or a negative number? Negative number, and that negative number is ridiculously tiny, right?
Something like that.
No, it's not something like that. It's exactly that. And so it's infinitely tiny. So anytime you say 1 or 5 or 2 or whatever, constant number divided by ridiculously small, you get an infinity. But since it's negative down there, we get a negative infinity. So to the left of 5, my graph looks like this. That's the wrong color. Let me change that. Getting ridiculously close. Now, allow me to go to the far left of 5. Instead of just to the left of 5, let's go to the extreme left of 5. Let's plug in a number mentally, like 10 quadrillion. Okay? Negative 10 quadrillion, because I said I'm going far left, right? Negative 10 quadrillion minus 5 is, well, basically still negative 10 quadrillion, right? Something ridiculously large and negative. Well, anytime you divide a constant by something ridiculously large, it's the exact opposite of dividing by something ridiculously small. If dividing by ridiculously small gave me an infinity, what does dividing by ridiculously large give me? If you had to think about it like this, let's not talk about the fact that it's negative for a moment. Let's say I have $1, and I have to take this dollar and I have to split it evenly with everybody in the school, how much do we all get? A fraction of a cent. Now let's say I had to divide it evenly amongst everybody in the country. Now I have to divide it evenly amongst everybody in the world. Basically what I'm getting at here is the bigger the bottom gets, the closer we get to getting 0, correct? But we're going super far left. The bottom is negative. So you're getting ridiculously close to 0, but it's still negative. So it looks like this. You see, you'll never get 0 because 1 divided by a number can never equal 0. It's not possible. And we've already said if the bottom was a positive, really, 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 really big number, we're ridiculously close to 0, just on the other side, because it'd be positive, right? 1 divided by 10 quadrillion positive is darn near 0. Now let's get really close to 5, but to the right of 5. How about a number like 5.000000001? It's a little bit bigger than 5. If we subtract 5 on the bottom, do we have a positive number or a negative number? Positive, but it's ridiculously small, right? So I have positive 1 divided by positive ridiculously small. Like that. Shoots up to positive infinity. So this reciprocal function has a vertical asymptote at x equals 5 and a horizontal asymptote at y equals 0. So our domain, which we've already written, is everything except for the number 5, and our range is everything except for the number y equals 0. Negative infinity to 0, hop over it, 0 to positive infinity. We good with that idea? Reciprocal functions will always look like that. Yes, Brian?
Alright, but how do you know why did you jump over that was using on B but not A?
Oh, okay. So the reason why I have a union in the domain here, and I don't have one in part A, is because this isn't a square root. I'm allowed to divide by positive numbers. I'm allowed to divide by negative numbers, which is both sides of 5. I'm just not allowed to divide by 0. That's why. So this union basically allowed me to include the left side and the right side of the number 5. I can plug in numbers. Well, I'm sorry, up here. I'm allowed to plug in numbers to the left of 5, which is what this says. I'm allowed to plug in numbers to the right of 5, which is what this says. But I have to put a little union there because I can't include 5. Now this one is a square root. You can't take the square root of negative numbers. So nothing exists to the left of x equals 5. If there's a square root sign, you can't have negative numbers underneath it. Let's just go with that route. Because the next question is a combination of the two. It's 1 divided by the square root of x minus 5. So let's talk about the 2 rules. This is part C. Rule number 1, what's underneath a radical cannot be negative, right? So the fact that I have a radical here tells me inside must be greater than or equal to 0. But then I also have a fraction. 1 over some stuff. It has its own rules. That rule is the stuff underneath cannot be equal to 0. Both of these rules must be followed. So I cannot say that the radical is allowed to be greater than or equal to 0, because if the radical equals 0, I'm dividing by 0. Instead, what this gives me is a domain that says, like, so if I have 1 over root stuff, then the stuff must be strictly positive. This way I'm never dividing by 0, and I'm never taking the square root of a negative number. So what would that graph look like? I told you anytime you're dividing by 0, you have a vertical asymptote, correct? That's what I told you. So there is still a vertical asymptote at 5. That has not changed. If you combine the two rules that we had for part A and part B, what you get is that the stuff, x minus 5, must be strictly greater than 0. So you add 5 to both sides, you go, oh, x is greater than 5. Well, there's your domain, from 5 to infinity. That means I can only go to the right of 5. So take a number just to the right of 5. 5.01. Yes?
So is the reason we put a parenthesis with the 5 because it's greater than?
The reason I put parentheses is because it's greater than, because I can't plug in 5. Because if I plug in 5, I'll have the square root of 5 minus 5 on the bottom, which is a big fat no-no. So if you take a number just to the right of 5, and then you subtract 5, you get a positive value, right? But it's small. And then you take its square root. It's still really, really small. And because you have a positive number divided by really, really small, you're coming from the positive infinity range. And then as x gets really, 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 really big, you're dividing by something. So like x is 10 quadrillion. Well, 10 quadrillion minus 5 is still nearly 10 quadrillion. You take the square root of it, it may not be as big, but it's still somewhere in like the billions range. And $1 divided by billions of people is positive, but it's almost 0. So the domain is to the right of 5. The range is above 0. And the homework is on Blackboard. The last example, you were just going to graph it with a calculator and do all the same stuff that we just did. That's all you were going to do. So graph it on Desmos, and you'll be able to see the domain and the range.